Welcome to MOVI-C Cabinet and Decentralized VFDs 201. This is session 14, Positioning. We've come a long way. We've covered a lot of content, but we're in for something new and something big. We're going to learn how VFDs can do something different from just running the motor at a certain speed. We're going to look at positioning, where the motor instead moves the application to some specific location and then stops. Let's get into this. You've been through a big drink or two, and you've been through a giant hamburger. This isn't quite as bad. It's not a big drink, but it's still a lot of material. Let's call it a tall drink. After all, positioning is complex. Let's define a few terms first of all. Positions are specific displacements along a line or specific angles around an axis. Positioning applications usually require translating the motor's rotary motion into linear or angular motion. Let's see how this can be done. Here's an example of a linear positioning application, a storage retrieval system. These are often used in warehouses. You have sort of a mobile forklift that moves back and forth and up and down next to a very big shelf divided into lots of sections, and then the fork reaches in, pulls out a pallet, delivers it somewhere. This is a linear application. Everything moves in a straight line. There are three axes, X, Y, and Z. The motor's rotary motions are turned into linear motion using perhaps gearing in a track or a belt system or a screw drive. There are lots of ways to do this, but this is linear. On the other hand, we have rotary applications that involve positioning, such as this turntable. It's used in a conveyor to change the direction that something is moving. In this case, the table turns to specific angular positions. An important note here, MOVI-C VFDs by default use the rev as their positioning unit. Rev stands for revolution. By default, positions are specified in 1/100th of a rev, 0.01 revs, and we have two pseudo-decimals. Now, what do I mean by this? Well, this ties into the fact that MOVI-C VFDs cannot accept decimal fractions when they're operating. Instead, you give them an integer, and you just have to remember where the decimal point is. So, for example, if you want to tell your VFD to position the motor to 837.29 revs, you give it the number 83,729. The VFD knows there's a decimal place between the 7 and the 2, and it acts accordingly. Don't let this throw you. If you forget about that imaginary decimal point, you're going to have some problems. Now, you might be thinking, well, I'd rather use standard metric units for positioning like millimeters. Well, that is certainly possible. It's very easy to work in those if you wish. And it is also possible to create user-defined units and even change the precision where you have more or fewer decimal places. We won't get into that in this session, but in our final lab session, we will explore both user-defined units and different precisions. Positioning requires some special hardware to make it happen, and I want to be sure you understand how all these key components work. So this is going to be kind of a survey of positioning equipment. We're going to start with a new term, and that is drivetrain. The drivetrain is everything that helps produce the motion. For example, you must have a motor to have a drivetrain. Now, you don't have to have a brake, but you certainly need a motor. But you might also have other things like a gearbox to scale the motion up or down. You might have additional transmission or drive mechanisms, in this case a toothed belt drive. If you're doing positioning, the encoder is an obligatory part of the drivetrain. If you're doing a velocity application, it isn't. This isn't a physical component, but it's something that is equally important. That is the control mode that the VFD is operating in. CFC mode is your best mode for positioning. It gives you the most precise results. You might have an additional encoder of some kind, like this laser encoder, and you might have some kind of custom unit. So these are all things that make up that drivetrain. Just a reminder, for most applications, everything is optional except the motor and the control mode. But that encoder is pretty common, and it's a necessity in positioning applications. Drivetrains, as you already know, are built during startup. Now, you've been creating very simple drivetrains with just the motor, the encoder, and the control system. But as you see here, you can add in additional components later, like a gearbox, a belt drive, and a custom unit. We'll explore this more in a later session, but I wanted you to see it here. Another important note, control cabinet VFDs actually allow you to configure two separate drivetrains. They're called DT1 and DT2. You've probably been noticing them already as you've seen those two columns. We've done everything in DT1 and ignored DT2. What's that all about? It's an optional feature. You don't have to use it, but you can switch back and forth between them in a number of ways. This can be useful if you want to run a motor using two different profiles, or you actually have two motors that are switch selected, one or the other is active at a time. By having two drivetrains, it's easy to do that switch over. Something you might use, but don't worry about it if you don't have an application for it. And a little mention here, the decentralized VFDs don't have this feature, they only support a single drivetrain. I've mentioned encoders and resolvers a number of times. These are feedback devices. We've looked at encoders in the context of precision speed control, but when you're doing positioning, you really need that feedback not just to maintain an accurate speed, but also to be able to move to specific locations. So the VFD needs an encoder or resolver to do this. Now, there are a number of different encoder and resolver technologies. I'd like to just summarize these briefly. One of the most popular encoder types is the incremental encoder. It is a relatively affordable encoder. It outputs what are called increments. These also go by the name of pulses or clicks. So you get these electrical clicks coming out, and the VFD counts them and times them, and based on that, it can do speed control and positioning. Many of them are optical. This one is. You can see it has a rotating disc with tiny little black lines on it. A sensor over the disc can see these, and as the disc turns, the black lines generate the clicks. A second type of encoder, and this one is a lot more expensive, is the absolute encoder. Instead of outputting clicks as it turns, it outputs position numbers. So as it rotates, it starts at position 0, and the numbers go up as you rotate it. This particular encoder outputs numbers from 0 to 4095 as it turns. Now, what happens when it gets back to the beginning? Does it go back to 0? Well, single-turn absolute encoders do exactly that. They go back to 0 when they've completed a full rotation. But the picture here is actually a multi-turn encoder. It can keep track of multiple rotations and generate unique position numbers up to several million positions. As you can guess, absolute encoders are excellent for positioning. Many of them will also generate increments, so the VFD can use those for speed control. And then finally, we have the resolver. This is an affordable alternative to an absolute encoder. It outputs position values, it gives acceptable positioning information, and also speed control. You can think of it kind of like a medium resolution absolute encoder, but it uses totally different technology from the traditional absolute encoder. Now, each feedback device has its own method of generating data. As I mentioned, many are optical. They have discs that look like this with black lines on them. This is an incremental encoder. And if you look at it, you can tell there are actually 3 tracks on it. The outermost has just a single mark on it. That is called the index or zero pulse track, and it indicates when the encoder is at its start position. Then you have 2 identical tracks called the A and B track. They have the same number of lines on them, but they're offset from each other. If you have 2 tracks, you not only can derive the speed at which the disk is turning, but you can also work out its direction based on which pulse comes before the other. That's why we have 2 tracks. Absolute encoders are more complex, as you can guess by looking at this disk. This one has an index track. It also has an incremental track, which can be used for speed control, but the position numbers are derived from the position tracks. Now, this has 7 position tracks. The light and dark areas generate a 7-bit binary number. Now, a 7-bit binary number has 128 possible combinations, so this disk will give you positions from 0 to 127. That's not actually very many. This is a low-resolution absolute encoder, but the disk is easier to understand. The resolver is an analog device. It's a series of coils, one of which rotates inside the other. It is energized with high frequency alternating current, and it outputs two analog signals that look something like this. The VFD digitizes these, turns them into numbers, does some trigonometry with them. From that information, it derives the position. Okay, well, that's the hardware. Now let's talk about something else that's very important with positioning, and that is something called referencing. Referencing is something you must do before you can begin a positioning operation. It's actually rather complex, so it's going to take a few minutes to explain it. Referencing is also known as homing or zeroing. Its purpose is simple. Find the location of the machine zero position, or MZP, in the application. Every application has a location known as zero, and all positions are based on this location. Positioning applications must be referenced at least once. Now, if you're using incremental encoders, they must be referenced every time they're started, because when you turn off the VFD, you lose the position. An absolute encoder always knows where it is, and so generally it only has to be referenced at installation time and if you make changes to the machine. Regardless of your encoder type, the routine that the VFD uses to locate the machine zero position is called the referencing type, and we're going to explore the referencing types that MOVI-C VFDs can use. Now, in order to find the machine zero position, we need to use sensors to help us locate it. A very popular way of finding the machine zero position is just to use the limit switches that the application may already have. As you know, limit switches are meant to prevent motion outside legal limits, but they do have known positions, and therefore the VFD can use those to find zero. All you do is you run until you bump into the limit switch, then back away from it, and at that point you're referenced. Remember this, limit switches are active low sensors, so they will be high when you're not touching them, and they will go low when you hit them. Now, remember that index track on the encoder? Well, that can be used sometimes for referencing. You just rotate the encoder until the index track goes by and generates a pulse, sort of like this. It may take up to a full rotation, of course, to find this location. We call this zero pulse detection. It gets the encoder in a known mechanical position. Now, by itself, it's usually not useful, but it's often paired up with other sensors when referencing, so I wanted you to understand how it worked. A very popular way of referencing is to use something called a reference cam. This is a contact sensor, and it's placed somewhere within the travel space. In this example, it's in the middle. A reference cam is active high or normally open, unlike limit switches, which are just the opposite. So when you tap it, it will go high. You can use the cam by itself. You can use it with limit switches and or zero pulse signals. Let me show you an example of using cam referencing. Notice that the cam is going to start low and it will go high when we touch it. So what we do is we run until we touch the cam. When it goes high, the VFD stops and then backs away from it just until it goes low when you clear it. And then it declares itself referenced. That's a very simple way to do it. Let's add a zero pulse to this using the zero pulse track on the encoder. You do essentially the same thing. You run up to the cam, you touch it, you go high, you back away from it just until you go low, and then you continue turning until the zero pulse occurs, and then you stop. All right, just a different way of doing it. They each have their place. MOVI-C VFDs have two configurable speeds for referencing. We call them search and retract. Search is usually faster, retract is usually slow for precision. We'll be looking at those when we do our lab. And an important note, for all the examples I'm going to show you, consider left counterclockwise and negative to mean the same direction, and right clockwise and positive to mean the same direction. MOVI-C VFDs support 10 different referencing types. Now, this may feel a bit overwhelming, but actually many of them are paired up, and that's because they're identical except the direction that they search. Some also can optionally use the zero pulse or not. In reality, there are only 6 main types to have to pay attention to, so we're going to look at each type, and it actually won't take too long. Here's type 1. Its goal is to wind up to the left of the first zero pulse encountered. So in this case, all you do is you run at the slower speed until you get the zero pulse, and then you stop. sort of like this. All right, that is one referencing type. Here's another. These both use a reference cam. The only difference is which side of the cam you wind up with when you're finished. So let's look at type 2, where you wind up on the left side. You run at the higher speed until you contact the cam. You keep moving at the slower speed just until it releases. So sort of like this. Touch it, move through it, but do it at the lower speed. You clear the cam, you stop. Optionally, you could have used the zero pulse, but we didn't in this case. Type 3 would be identical, except it would move in the opposite direction and end up on the other side of the cam. Type 4 and 5 use the limit switch. Type 4 goes to the right limit switch, and Type 5 goes to the left. We'll do Type 4, we'll go to the right. What you do is you run at the higher speed until you touch the limit switch, then you back off it just until it releases, and you do that at slower speed. You keep moving until the next zero pulse, and that's that. So here we go. Touch it, back away from it, stop. You're referenced. Type 7 and 8 use a reference cam that is usually located somewhere near one of the limit switches, just in front of it. We'll look at Type 8, where we go to the left side. You run at the higher speed until you touch the cam, and then you reverse direction and back off it at the lower speed. Here we go. We go at the higher speed, we touch, we back off, we stop. Type 9 is an interesting one because all it does is tell the VFD wherever you currently are at this moment, consider that 0. This is used sometimes in lab activities because we don't actually have to run the motor to reference it. In fact, we've already done that a few times when we were tuning our drive. We clicked that reference button and you just heard a brief click, and that was it. That was actually type 9. But in real applications, this is used where the machine has a 0 mark somewhere, where you manually move the application to that location, or you jog it by hand, and then you trigger referencing mode and say, okay, where you currently are is 0. The motor is not energized when this happens. It's totally manual. So you just manually move it to wherever 0 is. Once you get it there, you trigger this mode and you say, okay, that's 0. Pretty simple. And then the last type is called hard stop referencing. Instead of limit switches here, you have physical hard stops at each end, and all you do is you run the application into the hard stop until the torque climbs. You then stop it quickly and say, okay, I'm against the hard stop, I must be referenced. We'll look at type 11, where you go to the left hard stop. This isn't actually as brutal as it sounds because you run into the hard stop at the lower speed and you stop pretty quickly when the torque spikes. So kind of like this, you touch the stop, the torque goes up, you stop the motor and say, okay, I'm referenced. And that is it. We've covered all the referencing modes. Now we need to move on to something else, which is potentially a little confusing, but it's actually very important, and that is something called reference offsets. So what is a referencing offset? Well, by definition, it's the distance between the referencing sensor and the machine 0 position. Now you might be thinking, well, wait a minute, isn't the sensor always at 0? And the answer is sometimes, but not always. Let's dig into this a little more deeply. Sometimes, in fact, the referencing sensor really is at the actual machine 0 position. In this case, for example, we have a referencing cam, and let's say it's sitting right at the MZP. Now, if we've just referenced our application, it's moved to the cam, it's touched it, it's just backed away, and it's stopped, it is currently at 0. So we would say its reference offset is 0 as well. In other words, there's no difference between the location of the cam and the MZP. But there are situations where the sensor is not at the MZP. Here's an example. We have a referencing cam sitting in front of the right limit switch, but the MZP is here in the middle of the track. It is in this situation that we need to take advantage of reference offsets. So the reference offset is simply the distance between the sensor and the MZP. We measure it in some way. In this case, let's just say it's 28,504 revs away. That's the distance, but we need to include something else that's very important, and that is the sign. We make this number positive if the sensor is to the right of the MZP, and we make it negative if it's to the left. In this case, we'd use a positive offset because we're to the right of the MZP. We'd use positive 28,504. Let's see how both of these scenarios work. We'll start with a case where the sensor and the MZP are in the same place, so we set the reference offset to 0. Now, if we've just referenced our application, the VFD will report the current position as equaling 0. And if we give the VFD the command, go to 0, it's not going to do anything. All right, so that's our first scenario. Now let's look at the other situation where the MZP and the sensor are in different places. Again, we have a distance of 28,504 revs away. It's to the right of the MZP, so we make it positive. We set our reference offset to positive 28,504. We reference our application. We're right past that cam. And you might think, well, what's the position? Is it 0? The answer is no, it's not. The current position is 28,504 revs because that's where we are relative to 0. And if we tell the VFD, go to position 0, here's what it'll do. It'll zip over here until it goes to the MZP. And then at that point, it will report the position as 0. So I hope you understand that. We often do this in applications where it's mechanically better to have the 0 location and the sensor in two different places. Sometimes this is done to make maintenance easier, for example. Lots of possibilities. All right, with that out of the way, we need to talk about how we configure referencing. Referencing, like all other motion operations in the MOVI-C world, comes back to an FCB, FCB12. We go to the Functions menu, Drive Functions submenu, and we pick FCB12 Reference Travel, and everything is set right here. We set the referencing mode that we wish to use at the top. If we wish to use the 0 pulse, we can turn this switch on. If we want an offset, we can set it right here, otherwise set it to 0. We set the search and retract speeds in this location. Remember, the retract speed should always be slower than the search speed. And then finally, we have dedicated acceleration and deceleration ramps for the search and retract speed. Generally, you want to set these to a fairly high value so you reference very precisely. And that is all you have to do to get configured for referencing. So at long last, we can move on to positioning, except we need to talk about something else connected with positioning, and that is something called lag error. When you're positioning, the VFD knows where it's trying to go, it has an idea where it should be, and it has exact information as to where it is from the encoder. Now, if you have too big a difference between the expected and actual positions, you have something called a lag error situation. The VFD does not want to allow excessive lag error to occur because if it does, it could mean something is jammed, something's stalled, you have some kind of mechanical malfunction. In most cases, the VFD will fault if the lag error is too big. So how big is too big? Well, you decide that. You set it right here in FCB 9, and you go up to the lag error window and you set the value right here. Now, by default, it's 1 revolution, so if there's more than 1 revolution difference, you're going to get a fault. If that is too little, you can increase the value, certainly. You could make it lower if necessary. This is application dependent. And then right down here, you tell the VFD what you want it to do when a lag error occurs. We get that set, and now at long last, we can move on to positioning. There are two main linear positioning modes. The first is called absolute positioning. The idea here is that all motion is relative to the 0 location. You can think of the travel space as a gigantic ruler. The MZP is the 0 location, and you have positive and negative values moving to the right and to the left of it. When you tell it to go to a location, it simply goes to that number along the ruler. So if I say go to 1,000, it'll go right here to positive 1,000 and stop. If I say go to 1,000 again, it's not going to do anything. It's going to say I'm already there. And if I say go to 1,500, it will move here. If I say go to minus 2,000, it will zip back to this location. So you see we're just going to the numbers along the ruler. Very simple and straightforward. Now our second positioning mode is called relative positioning, and this is a little different. Instead of going to specific locations along the ruler, you always move a certain number of units clockwise or counterclockwise relative to where you currently are. Right now we're at 0. If I say go to 1,000, and that's positive 1,000, it's going to move here. It's going to move 1,000 units clockwise from where I was, which was 0. Now, up to this point, this is really no different than absolute positioning, but here's where the difference shows up. If I say go to 1,000 again, it will now move to 2,000 because it's moving 1,000 units clockwise from where I was, which was at 1,000. So we're different here. And then if I say go to minus 2,000, it's not going to go to the minus 2,000 location along the ruler. It's going to move counterclockwise 2,000 units from where I am, which will actually bring me back to 0. So that is the difference between absolute and relative positioning. They are both used. It just depends on the application. We give you both. And with that, our tall drink is over. We have completed our positioning introduction. In our next session, we're going to look into MOVI-Kit positioning drive, and we're going to do some actual positioning. See you then.